2 of our Varahamihira Science Forum. We are in the sixth year of our journey. Thanks to all of you for your support. We have had in-person live sessions to begin with for the initial 2-3 years before COVID struck. We switched back to the online mode for a couple of years. Then we got back to live sessions for a few episodes this year. Again, we have switched back to the online mode for this session today. Very happy to welcome you all to today's session. And today's session is to be delivered by our founder, Rangaratnam Gopu. I'll give a very brief introduction to Gopu. Of course, the regulars of Varahamihira Science Forum, you don't need an introduction to Gopu. For the record, Gopu is a former software engineer, and of course, he's one of the founders of Varahamihira Science Forum. He obtained a BE in computer engineering from Arulmigu Kalasalingam College of Engineering, Srivilliputtur. Thereon, he pursued his MS in computer science from Texas A&M University in the US. This was all back in the early 90s, late 80s, early 90s. He worked in the software industry, which included a 5-year stint at Microsoft. So thereon, he became interested in history, economics, astronomy, linguistics, epigraphy, literature, heritage, culture, many more. And he's been a volunteer for the Tamil Heritage Trust for several years now. Some of his essays on science, heritage, arts, and history have been published in newspapers and magazines like The Week, The New Indian Express, and Swarajya. Currently, he also teaches at Savita Engineering College in Chennai. He delivered our inaugural lecture, the first lecture in our Varahamihira Science Forum. It was on Antoine Lavoisier and the origin of modern chemistry. And thereon, he also delivered a talk on James Watt's steam engine. Both of these talks were in English. He also delivered a lecture on astronomy of ancient cultures in Tamil. All of these for our Varahamihira Science Forum. He's also spoken about Indian astronomy and mathematics and mathematics and astronomy of ancient cultures. Again in English as well as in Tamil. English at Tamil Heritage Trust. He's conducted courses on Indian astronomy and mathematics at our Varahamihira Science Forum. I'll hand this over to Gopu now. Before that, a very brief introduction of Varahamihira Science Forum. Again, of course, many of you are regulars at our forum. We started this forum back in 2017. August 2017 was when our first lecture was delivered by Gopu, today's speaker. We thought that, in Madras, which is considered the cultural capital of South India, there have been a number of sabhas and organizations which are into promotion of arts, music, especially Carnatic music, classical music, theater, and dance. There are so many venues, so many performances, lectures, and demonstrations. All of these happen on the cultural space. Whereas when it comes to science, it's predominantly restricted to academic institutions such as the IITs and maybe perhaps the engineering colleges, which might host some seminars on topics, technology topics. But all of these are primarily for a niche audience of academicians and students of the colleges. Rarely you see that lectures on science and technology happen in the public sphere. And that too for a general audience, which may be interested in science, but not necessarily are coming from a science background. So we thought, we could create a forum where we could bring in professionals as well as amateurs and enthusiasts who are interested in science to give lectures and give presentations on topics, varied topics in science and technology. And therefore, there is a forum for the general public, the common audience, to come together and deliberate on topics of science. So that was the motive behind some of us joining together and starting this. And when we started this, we weren't even sure if we would, the forum would last maybe some 4 or 5 lectures. But thankfully, due to the support of all of you, we are into the 6th year of our existence, and today's lecture is our 62nd. So huge round of applause goes to all of you. And of course, thanks to our team, primarily Gopu, Badri, Ramanan, SL, Mohan sir, and all of the members. Thanks to whose contacts we are able to reach out to many professionals, amateurs, and enthusiasts and organize these talks over the last 5 years. So with that short introduction, I'll hand this over to Gopu now on today's topic, which is evolution of computers. And a computer engineer himself, Gopu, I think it's very appropriate that you speak about this. Over to you, Gopu.
Thanks, Harvey.
One second. Yeah, go ahead, Gopu.
Thanks, Harvey. I'm happy to speak at Vara Mera Science Forum again on my field of professional education and experience. I had visited the Computer History Museum in Mountain View, California, which is very close to Google's headquarters a few years back. So I'll be using some of those examples, some of the pictures from there. And let me start sharing the stuff. So I thought everybody's using computers. We could have a talk on this particular topic. So is that visible? Okay. I gave it a mildly interesting subject. These are photographs from the Computer History Museum in California. I called computers electrified mathematics and numerized languages. And as I go down the presentation, you'll see why I called that. I start off with a little bit of a quiz. It's just since nobody is responding, it's just kind of a self quiz at this point. But if you name some of the most influential or most familiar devices that we use, you can usually name an inventor, or at least you can associate somebody with it who you think is the primary inventor. So devices, and basically I'm talking about mechanical, electrical, electronic devices, physical devices that we use all the time, like the steam engine, telephone, bulb, and all this, electric bulb. So if you ask about the steam engine, you can say somebody like James Watt is the person who comes to mind. The telephone, Alexander Graham Bell, electric bulb, Edison, air conditioner, airplane, Wright brothers, radio. These are the famous names. But if you ask about computers, who invented a computer? Generally, there is a little bit of a thought. A popular answer is Charles Babbage. Some people think Alan Turing, other people say John von Neumann. You have other excuses and names on such things. But if you look at it to be in an objective way, no single person really invented the computer. A number of devices, ideas, technologies, projects, all of these came together over several years from different companies, institutions, labs, and even across countries to create what we use today, which is the digital electronic computer. So what is a computer? The computer, the definition of the computer or the meaning of what the computer is has changed a little bit over the years, over the decades, as it's increased in functionality. So today we could say that an electronic computer consists of hardware and software, really both of them define it. And among hardware, you would be familiar with these components, what's called a central processor or a CPU, central processing unit. Memory, which we call RAM, internal memory. Then there is something called external memory. Now we have hard disk, magnetic tape, CD. These are the slightly older ones. Now we have like solid state devices. It's actually, we call it external memory even though it is inside the computer because it's not part of the basic layout of the computer. It was really an additional unit added later. Input-output devices. These are things that we are most familiar with, but actually the first computers didn't really start out with very good input-output devices. So these things developed after the early computers: keyboards, your television screen, monitor, touchpads, punch cards. The punch card is one of the earliest one. It's not even a very user-friendly one, but it is one of the, and that punch card is actually came before even the computers. And today computers are, you can't think of a computer without communication systems. You have modem, you have Wi-Fi, Bluetooth, and all kinds of other such similar devices. So that's kind of the hardware aspect of it. Connecting the computer to the internet. But the internet has been in vogue only about 35, 40 years. Most computers were isolated systems for a long time. Then you have software. Everybody knows what an operating system is because we all use, Windows or Android or something like that, or Linux or whatever. And then there's this, even this has now become a familiar word because of the word app. You have a mail app, you have a Twitter app, you have a Facebook app, mostly social media or apps now, but you have all kinds of apps, right? You have banking apps and word processors and spreadsheets and so on. And so that's an application software. And that comes from the computer. And really your modern cell phone is just, it's a computer that, that also happens to be something that you can use as a phone. I said electronic computers, but the history of devices to compute or help people calculate is much, much older. Really, you can, using archaeological objects, you can actually go back to this object on the left, which is really a clay tablet from Sumeria, which is modern day Iraq. One of the most ancient civilizations, they used clay to write, and they used a little thing called a stylus. It's like a little wooden stick or a metal stick with a little indent at the bottom, and you make marks on the clay and you record it. Those of us who have seen some of the seals of the Harappan civilization know that the Harappan civilization also used that. So baked clay is the material of the earliest writing, the earliest calculations and computing for which we have a record. We may have had computing before that, but we don't have physical artifacts that show that. People may have talked orally about numbers and things like that, right? But physical evidence of that comes from these clay tablets in Sumeria. And from that we come to this. This is actually a silicon wafer. It's a wafer of silicon. Silicon is really comes from silicon dioxide, which is sand. It's a primary component of sand. And the silicon chip, a silicon wafer, each one of these little squares on this is a silicon chip. It's an integrated circuit, or what you want to call it today. It could be a processor, it could be memory, it could be something else. These are silicon. This is a silicon wafer with a lot of silicon chips. So we went from baked clay to baked sand or baked silicon. And I'll briefly look at some of the development of the computing devices from that. So some of the oldest computers we have evidence for is from Europe, cannons. Actually, even older than this are the abacus that's used in Japan and China. Very simple calculating devices with rods on beads. People still use them in schools and all that. But here is a slightly more complicated device. They use certain angle indicators, like these things are called quadrants, and later on they're used in shipping to actually calculate what the angle of the cannon should be to fire at a target and succeed in bombing it. And so we have a very woodcut. This is a woodcut print. This is actually in the Computer History Museum in Mountain View, California. Most of the pictures I'm using are from their museum or from their website. And this one helped calculate the angles, and you had other things like this. So it's a mathematical instrument that were used, and at that point they called it, it was a computing device. Slightly more sophisticated devices were invented by John Napier, as an Englishman in the 1620s. He is famous for inventing logarithms. We sometimes use logarithms, right? The inverse of an exponent. And Napier says his logarithms were inspired by India, though we don't see much about India. No, we don't hear much about logarithms, Indian contribution to logarithms. He came up with something called Napier bones, which actually nothing to do with logarithms, perhaps something to do with logarithms, but they are actually computing devices. They are calculating devices. Literally a small device to use, do little calculations. A little more effective one is actually a practical one called the Pascaline adder, named after its inventor, Blaise Pascal. Most of us may have heard of Pascal as a mathematician in France, He was around the same era as Napier, 1640, a few years before Isaac Newton. And he was a tax collector, and his father was also a tax collector. And so he wanted, they were doing a lot of writing. Any accountant would understand this. They're doing a lot of computing on paper. And this was very tiring to him. So he wanted to do a lot of calculations. He wanted a machine to do the calculations so he doesn't make mistakes. I invented a machine that to do the calculations. So he came up with a device called a Pascaline adder. I'm not going into any details on all of this. I'm simply mentioning that there are mechanical devices long before electronic computers. This is the period when electricity was barely understood. I mean, they just realized there's something called electricity there. The irony is that there is this bridge in Madras called Napier Bridge. It's named after a great-grandson of that John Napier. This is actually a governor, Lord Napier, who came much later. And this Napier came to India to write a history of mathematics. He never wrote it, but there's a bridge named after him. It's very interesting that we don't see much about Indian mathematics, but an Englishman came and we have a bridge named after him. Another interesting development was in a different field, not in accounting or taxing, but in textiles. You don't expect computing devices in textiles. But France in that period, actually all of Europe had mechanical looms, and the whole world had mechanical looms. They were mostly hand looms. They were there to weave fabric. You could weave cotton or linen or silk, and these were fine silk weaving. They had somehow managed to borrow the idea of weaving from China, and one of the looms was developed significantly by a guy called Jacquard, a Frenchman called Jacquard. In the late 1700s, in fact, in the early 1800s, because by the time he came to, invented this device, he was born in the 1700s, but he invented this device in the early years of Napoleon's rule. These cards are literally a way to, choose which threads would go into the pattern of the weave. If you've ever seen a weaving machine, I'll show you one. You have threads going longitudinally, and you have transverse threads, and these threads keep coming forward, and then you add one horizontal thread to that each time. And which thread should you add? What color should it be? What pattern could be? And each of those threads is suspended from the top of the loom with a needle, and the pattern, the punch card would have either a hole or not a hole. If the hole was there, the needle would go through, the thread would go through. There's no hole, the needle couldn't go through, the thread couldn't go through. And the pattern of the punch card determined which threads would go in and which threads would kept out. And this would determine the textile pattern that could be created with this weaving machine, the loom. And they could do very sophisticated, very beautiful patterns. Look at this. This looks like, a painting, but it is actually a piece of cloth woven with a Jacquard loom. It's absolutely a marvel. And that was done using these punch cards. Now, this simple technology of punch cards is still used today. Even today, I took this photo a few years back, 3-4 years back in Kanchipuram. This is a weaving center there. It's a textile loom, and you can see that the threads are here in a longitudinal way, and then here are the threads. This shuttle that goes back and forth weaves the cloth, and all these needles are coming through these punch cards, and whichever is coming through is allowed, and whichever is not is determined by the pattern, and the pattern is set by these cards over here. And this is a close up of those cards, and you can see in some places there are holes, in some places there are no holes. And then depending on that, the threads will come through or not come through. And that's what causes the patterns on the textile. So what does this have to do with computing? It sounds like just like something to do with textiles, except these punch cards came in useful about 80 years later in the United States. The United States, the founding fathers of the United States, the people who wrote the Constitution, ordered that their government take a census of their entire population every 10 years, understand their economic condition, the spread of the population, social condition, etc., so that the government could serve the society better. And so every 10 years, they're supposed to do a population count. and there was an entire government department dedicated to this. And by the time it came to 1880, they were collecting so much data for the census department to prepare a report. It was taking longer than 10 years. So it would seem that the 1880 census report that is supposed to be submitted to the government would not be ready by the time the 1890 census had actually started. So this was a moment for panic for the government, and the bureaucrats said we need a better way to process, we need a faster way to process, because the population of America also went from something like 20 million to 100 million within those years, and they had the railways, but the automobile had still not come along. There are no planes, so no computers, obviously. So computing all of this, a lot of this information was still computed by hand, and they wanted to see if they could automate it. So one of the ideas that they had was to record population data on punch cards. So just like you see this pattern of zeros and ones, because zero could stand for, a one could stand for some, just this is numbers, right? So a person's age, a person's gender, a person's height, weight, social status, economic, income, all of this could be recorded series as a series of data, digitally on these punch cards. And then there is this person called Herman Hollerith who made these machines called Hollerith machines, and all these punch cards would be fed by clerks, the census clerks, in a sequence, and they would be all the data should be collected. That was the plan. This Hollerith company is the one that later famously became International Business Machines, IBM, the forerunner of the personal computer. And this is one of those Hollerith machines that they have the Computer History Museum. And so this is the kind of the adaptation of this is why the punch card of the textile loom became relevant to computing. Again, remember, this is a mechanical device. It's just it's a paper card with holes in it. It's supposed to be counted mechanically. And there are some more mechanical devices. Actually, lots. It's amazing how many mechanical devices were devised using levers and gears and little things like that, and little keys like typewriter keys. And based on existing inventions, people are making new devices. This one is actually from the USSR. It is called the Felix arithmometer, and it is another computing device. And I'm not going to it. But the most famous of these mechanical devices was actually one that was never fully built. It was built by a person called Charles Babbage. He just kept building and building, and they gave him a lot of money for a similar project in England in the 1840s. For several years, he was trying to build a computing device that would add and subtract and even do calculate. In fact, they were trying to do logarithms. He was going to use it for astronomy and other scientific applications. And the best way to do that was, he thought, to divide a mechanical device. In fact, it is not just going to be a mechanical device, it is going to be a steam-powered mechanical device. Okay. That Babbage never fully built it. It was just the technology was simply not advanced. He was trying to do it one person operation with just a couple of assistants. And so after a few years of funding it, they just gave up and then abandoned the project. It was actually fully built only in 2010 by one of the research heads of Microsoft, a guy called Nathan Myhrvold, and he built a couple and donated one to this museum. And so that's what you're seeing here. But long before mechanical devices, people have been doing computers. Now, should people be called computers at all? Egyptians have been writing, things on paper. The Chinese have been, papyrus. The Chinese invented paper. As you saw, the Sumerians used cuneiform recording on clay tablets. In India, we used, palm leaf and Bhojpatra and all that. We had professionals like Shreshtas and Kayastas and Kanakapillai and all these people. All these clerical people, each society, of course, called them by their local names. And this continued, well into the modern era. 20th century had vast offices of manual calculations, government, large businesses, not just census counting, but, companies with 100,000 employees and things like that, accountants, tax officials. All of these people are doing large numbers of stuff. And so, companies are getting bigger and bigger. And so you can't just do a personal clerk, but you need a lot of computing. And really human beings are doing this. In fact, a very, one of the organizations we considered cutting edge, scientifically cutting edge, NASA, National Aeronautics Space Administration, America's space agency, had something called the Jet Propulsion Laboratory, where they're doing research into jets and rockets. And for that, they needed a lot of calculus and they needed a lot of calculations. And so didn't have the mechanical devices are inadequate, though they had these devices like adders. They are mechanical adders, electromechanical adders, actually, some of them. And but the adders were just called adders, but the people who are hired to do this job of doing the calculations are called computers. We are looking, literally, they'd say we are hiring computers, and they meant humans. So we had mechanical computers, and we had humans who are actually called computers for life. Your job title would be computer, and you're expected to be somebody who computed a lot of stuff, wrote it down on paper, and submitted a report. And all your reports would be tallied up and passed on to the scientists for their calculations. And perhaps one of the most famous computers is a guy who did something like this. Ramanujan, who was a clerk in the Madras Port Trust. When he couldn't pass the exam, he joined the Madras Port Trust as a clerk, and that's where he was discovered as a great mathematician. He was literally doing this tedious manual work. By this period, actually, not just electronic computers, not just mechanical computers, but because of telegraphy and telephones, devices called electromechanical relays had been developed, and the relay is just an electrically operated mechanical switch, right? And it can you can turn a switch on and off mechanically. That's this kind of switch that we are familiar with. But that switch basically is just an insulator of the spring-loaded thing. It closes the circuit when you put it on, and it disconnects the circuit when you turn it off. And that wire going through that can be used to operate an electromagnetic coil, like this. This is kind of the simple format of an electromagnetic switch. So when current comes through, this coil is when you power this electromagnetic coil, what happens is it becomes magnetically charged. It attracts this metal, and this metal, it will contact here, so this will close another circuit. So you can use electricity in one circuit, using electricity in one circuit to operate a mechanical switch. Now that switch in turn completes an electrical circuit. So that's called a relay. A switch used to operate a switch. We are accustomed to switch used to operate things like fans and light bulbs and televisions and iron boxes and radio and stuff like that. But a switch can be used to operate another switch. And so people thought of a way to come up with make a computing device based on this electromagnetic relays. And these were already being used in telegraph and telephone systems. So one of the geniuses who did this was a person in Germany called Konrad Zuse. And Konrad Zuse came up with a computer. He named it after himself, Z1, Z2, and then later Z3. And this is Z3, which is the famous first real effective electromechanical computer. But that was the period when Hitler came along, and then he was stuck in that period. In the Germany, of course, suffered an enormous amount of damage during the World War, so he had to discontinue some of that work and so on. But the electromechanical relay idea was borrowed by other people, famously by the English researchers. They were using it to build their own electromechanical computers. And the most famous of them is actually this machine called the Colossus. It was at Bletchley Park in England, which was the headquarters of one of their encryption teams, deciphering teams. They were trying to break the German war codes. And this machine actually helped decrypt the words. There's a lot of processing power that was needed. And so they built a completely electromechanical device to do this. So while Zuse was building his electromechanical computer, these guys were building electromechanical computer to do decryption. For the English are there, can Americans be far behind? At Harvard University, Howard Aiken, a professor there, led a team, and they developed computers and that naturally called them things like Mark 1 and Mark 2. You can see this whole thing is the computer. You can see it's a very large room. Lots and lots of devices are there. It's a very large electromechanical computer. It has thousands of relays. And this is where they even had a little bit of programming on it. It had a little bit of memory, and I think they are trying to do some coding on it. And that's where one of those tapes in which they are feeding the data got stuck one day. And one of the assistants then, who would become a very famous person in computing, Grace Hopper, literally stopped the tape, pulled it out, found out there was a dead insect on it. and so remove the tape, substitute a better paper tape. And every time after that, when they were solving problems, she would call it, I'm going to debug the problem. And so that debugging became the term for fixing problems in computer software ever since. At this time, another device became possible. The electromechanical relay, of course, was nearly 70, 80 years old by the time this device was, these electromechanical computers were built. But a couple of new devices, transistors and triodes, even triodes are actually quite old. They are things called vacuum tubes. They came along. And so a couple of others at the University of Pennsylvania, Professor Prescott Eckert and John Maudsley, decided to build a fully electronic computer, not using electromechanical relays, but fully electronic relays, electronic switches. So it's not a mechanical switch, but an electronic switch. And they were using vacuum tube triodes and diodes for that. So this computer that they call it, actually, they really call it a calculator, electronic numerical integrator and calculator. And this name, they abbreviated to ENIAC, and this became ENIAC. This is just after the Second World War ended. And you can see this one is also like a room-sized machine with a lot of people at different points of the machine. The ENIAC, this is not the ENIAC, it's a different computer. The ENIAC had 18,000 vacuum tubes, but it had no software. Engineers and the programmers and engineers are not two different fields. Engineers literally programming was done by rewiring the connections. That's why I showed this picture. There are computers that look like this, it's a jumble of physical wires from one vacuum tube to another, one electric point to another, and so on. All kinds of complicated sockets. This one literally had 18,000 vacuum tubes. And the advantage of the transistors was that it was 1,000 times faster than the electromechanical relay-based computers, right? The computing speed of these things, because it was electronic rather than electromechanical, every computer, so in 1 second, it could do 1,000 times the number of operations that an electromechanical computer could do. And once they started successfully building this, that was the way to go. But this still faced a lot of challenges because the transistor had a lot of problems. The transistor would heat, some of them would fuse. You had to go figure out which was the transistor that burnt out. You had to go replace it. That was not a very easy task. So they had some challenges. Around this time, different company called founded by two people, Atanasoff and Berry, started the Atanasoff Berry computer, and they tried to patent it. They tried to patent the computer. And the ENIAC, the founders of ENIAC, naturally, went and filed a count of this thing, and then they went to court to resolve the patent dispute. Who invented the computer? Was it ENIAC or ABC? The US court then gave a formal judgment that the computer had too many components, so no individual could be given the credit for putting it all together. So they declared that computer cannot be patented because no individual can be given the credit for inventing a computer. So they have stored this Uniac at this Computer History Museum. I can't take very good photographs because of the reflective glass and all that, but that's what it looks like. Some parts of it at least look like in the museum. Followed by the, just around the time of the ENIAC, there was somebody else trying to do something called the EDWAC, and it had a similar name, Electronic Discrete Variable Automatic Computer. And they set up a committee to figure out how to do this. And the head of the committee was a mathematician called Johann von Neumann, or John von Neumann, as is, the English pronunciation of it. And Eckert and Maudsley, the builders of ENIAC, were also on the committee. But since von Neumann became the head of the committee, they came up with the layout of how a computer should be devised. And they said a computer should have what's called a control unit. A control unit would, fetch instructions and data from a memory unit. These are two different components in a computer, and then execute the instructions one by one. So one of the advantages of storing data electronically as numbers or as voltage points is that you can also store instructions as numbers, basically electrical signals and so on. So instructions and data can be stored in the computer memory, and the computer can, based on a clock that gives a signal, it can fetch, this control unit can just go to the memory, fetch the data electronically, one instruction after the other, execute it, and there is resultant data, it can put it back in the memory and so on. This structure of, having a program in the memory unit having a control unit, fetching instructions and data from the memory, and then doing some computing processing in the control unit, and then putting the data back in the memory. This is called the von Neumann architecture, whatever you want to call it. And that it became named because he was chief of that committee. There are some people who think von Neumann should get credit for inventing the computer, but he was really just the head of that committee. So let me explain what this is, because there is a little bit of a mathematics aspect to it. Before I get into the electronics aspect of the computers, let me go into the mathematical aspect of it. Because literally what a computer is just the electrification of zeros and ones. We went from zero to binary to what's called Boolean algebra, and from that to the stored program. Now, mathematics we've had for very, very long time, 6,000 years at least. We have some Sumerian mathematics at that period. We have Egyptian and Chinese records also of that period. Indian mathematics also probably goes back to that period, but we don't have any archaeological evidence, unlike the other three cultures, though we did a lot of things. We developed a lot of ideas also. And very early on, people came up with step-by-step procedures to do certain things. Even today, we use them without thinking of it as a step-by-step procedure. That step-by-step mathematical procedure later got the name algorithm. It's actually named after a country called Khwarazm. There's an Arab mathematician called Muhammad ibn Musa al-Khwarazmi. He's from a country called Khwarazm. That country no longer exists. It's now Uzbekistan, Kazakhstan, Turkmenistan, all those countries. It's split into different countries now. But that al-Khwarazmi came up step-by-step mathematical procedures for some elements of algebra, and that came to be known. The step-by-step procedure came to be named after him. He didn't invent it. Long before him, for several thousand years, Egyptians, Indians, Sumerians, Chinese, everybody had been developing these procedures. In fact, if you're cooking, you do step-by-step procedure. A recipe is really an algorithm, except an algorithm usually is considered given a name for a mathematical procedure. So step-by-step procedures in mathematics existed for a long time. Then India gave two very interesting contributions, very critical contributions. One was, of course, was the zero. We don't know who came up with it. And the other is something called the place value notation, which is using the same 9 digits plus the 0 digits, so 10 digits, to represent multiple numbers. So like this number 200 or 800 or 1250. This 1 here means 1000, 2 here means 200. This is what we call the place value system. Depending on where the place is, its value is determined. So this is a very useful system for mathematics. It dramatically increases the value of numbers, and the critical value number there for that is the number 0 and the digit 0. From that, some cultures understood that you don't need a base 10 or a base 20 system. You could actually have a mathematics simply based on binary system, where you don't need 10 digits, just 2 digits, 0 and 1 could do something. You could do a lot of methods, though it's tedious. It's not very pleasant to do that. It's much more convenient for human beings to do decimal or base 10 computing. From binary mathematics in the 1850s, around the time when Charles Babbage was trying to do a mechanical computer, the person called George Boole came up with a concept called Boolean algebra. Boolean algebra is just an algebra of logic. So it's not an algebra of mathematics, but it's an algebra of logic. So I'll look at that. And from this Boolean algebra came the concept of operating, coming up with logical operations using mathematics. And from there, with the development of information theory and understanding of representing numbers, not just numbers, but also data with numbers, you emerge the stored program concept of John von Neumann, which you just saw. The stored program concept actually probably was by von Neumann. So let us look at what Boolean algebra is. Boolean algebra talks about very simple things. I'm not going, this is a whole course if you are studying computer science. I'm going to summarize it in one slide because I'm just only talking about the basics here. You can make a statement, and the statement can be either true or false. Now, suppose you make two statements. So the statement can be, I am sitting down. That's true or false. I'm sitting down, so it's true. Or it can be false. You can say, I'm eating something. I'm not eating something, so that's false. So what is two statements? Suppose I'm saying I'm sitting down, I'm eating something. One of them is true, the other is false. So how do you combine that? And so you can use logic to determine what it is. Or you have three operators in logic. They are called the AND, the OR, and the NOT operator for logic. And you can have combinations of all of those. Think of it as like the plus minus multiplication symbol of arithmetic, And so the not is literally a negation. So not is, if somebody says something and you want to say not true, not that, then it's the opposite. So if something is true, the not of it is a false. If something is false, the not of it, the negation of it is true. So the not operator takes a statement and says, reverses its truth or falsity. Okay. The AND operator is a very simple one. The AND operator says a statement, a combination of two statements is true only when both statements are true. If both are false, of course it is false. If one of them is false, also it is false. But only when both are true, it is true. The OR operator says if one of them is true, then it's sufficient to be true. Only if both are false, it's operator is false. For the example, I can say, if I said I am talking, it's true. The opposite of that would be false. That is, I'm not talking. So the not operator of I am true would be I'm not talking. For this other statement, I am sitting down, I am eating. If I'm saying I am sitting down or I am eating, if I do the or combination, then I'm sitting down is true. So one of this condition is true. The other one is false. It doesn't matter. So A or B in this case is true. But I'm sitting down, but I'm not eating. So both of them should be true. One is true, one is false. So with the AND operator, the combination statement is false. So these are just simple ways of doing, I'm using statements to do this, but you can use this, for any representation of data and, use that. So now this logic of true and false, it's only two states, right? It can be true or false. And what two statements, obviously we can represent that also as 0 and 1. If you can represent true and false, say false as 0 and 1 as true as 0 and 1, then logic can also be represented using the binary number system. So not just mathematics, not just numbers, but logic and the combination of logic and three logic states can also be represented using binary system. So from that, this is where you get the Boolean algebra. You replace the true and false with ones and zeros. The same operators come through with the similar things. Instead of and, not, and not, you use 0 and 1. You use the same and, not, or not, except using 0 and 1 for false and true, and holding the tables exactly the same. Opposite of 1 is 0, not 1 is 0, and not 0 is 1. 0 and 0 is 0. Only 1 and 1 will be 1. So 0 or 0 will be 0. 0 or 1, 1 or 0, 1 or 1 will be true. So this is the concept of it. May seem very silly, very elementary what you do it with, but actually if you implement this in electronics, it turns out to have enormous advantages. In fact, all computers are based on this concept. So what does this allow? First, logic can be binary. It's true or false. Now voltage or electric current can also be binary, right? It can be high or low. It can be on or off. This is what a switch is. A magnetic state is binary. You take a magnet, let's consider this a magnet, this pencil cap. If it is pointing upwards, it's north and south. If it turns around, it's south and north. So it has a north and south. So you have a two states for that thing. So magnetic state is also binary. If numbers can be electric or magnetic, a machine can do math with electricity. How do you do that? You take one digit at a time and then you combine the digits, use electronic circuits, electrical circuits, and you can do something with it. If logic can be electric or magnetic, a machine can do logic with electricity. You can actually do it all with mechanical things also, which is what Babbage and others tried before. But now with electricity, you can do the same thing. And operations can be electric or they can be electronic. So which is where you get electrification of numbers. You take and electrification of logic. You combine mathematics with logic, you get a computer, you get your software, you get all your programming. That's exactly what it is. And words can be stored as numbers because you can just 26 letters of the English alphabet, 247 letters of the Tamil alphabet, 500 odd letters of the Sanskrit alphabet, whatever language you take them, you can simply give a code to each one of the letters of the alphabet and say this particular case is the, let's say 64 is 1, 64 is A, 65 is B, and so we have a sequence number. It's literally what one American standard code is represented as. You do that, you can store words or letters also as numbers. You can store letters, you can store words, you can store text, which is literally what you're seeing. Your PowerPoint presentation that you're seeing, it's all coded numbers presented and displayed into different things. Somewhere inside my computer, this A here, the title of all things binary, the A is stored as a 65, the L is stored as 65 plus 12, which is 77, and so on. So this is how the computers store numbers, and representatively they store us as numbers. In actuality, they are stored as electric status, positive or negative, high voltage, low voltage, or if they're stored magnetically, they're stored as north or south, aligned magnets. And with this, you can actually come up with something, a device called a logic gate. A logic gate is electronically a device called a flip-flop. Using a set of transistors or triodes can be configured so that data, it can actually store a value, either a 1 or a 0. And if it can store one binary digit, either a 1 or a 0, that binary digit is where the word bit comes from. And using these transistors or these triodes and all these other electronic circuits, you can actually create these logic gates where you can put two inputs, 1 and 0, or 0 and 1, or 1 and 1, or 0 and 0, and it will come out with an output. So you can design things that will always act like an AND logic operator, or an OR logic operator, or a NOT logic, and those are called gates, literally called logic gates. And you can combine logic gates to do multiple complicated, more compound logic. And with this, you can actually implement addition, subtraction, multiplication, and so on. That's literally how they use it. And the technology used can be magnetic relays, vacuum tubes, and later transistors. And literally, that's how they stored, numbers as data, numbers as electrical signals, then words as electrical signals, then instructions as electrical signals, an entire series of mathematical instructions, which is an algorithm. And then now we have a computer that can do calculations and present data in displays. So the combinations of gates can do magic math or logic. And really, this is one of the very first gates that was built. This was called the Model K adder, and he called, this is the person, George Stibitz, developed it. The adder is literally built with logic gates, and this is a very large device. You can actually input some data to it, and it will come up with a number, and it will be displayed the number as a light bulb. So the input would be a switch, to say 1 or 0. And the result would be shown, which the adder would add 1 and 1, or 0 and 1, or whatever it is, and it indicated using this light bulb. So this thing was called Model K because he literally assembled it on his kitchen table, so he called it Model K to sound kind of technical. That's 1 bit. It's adding 1 bit. It's adding 2 individual binary numbers. That's as small as that. How did we get that? We got that using mostly electronics, much more effective than electrical signals. But the electronics didn't develop right away. That electronics had a story. We had development from diode to triode to transistor integrated circuit. And this is a very fascinating part because of the computers. Electronics is a very interesting development. So I will trace out the development of this field, the electronics field, with specific relation to computers. So a diode or a diode is really what's called a semiconductor. We have studied that there are things called 3 types of devices. With glass, we have things. We have with light, we have things that are called transparent or opaque. If you take a glass or plastic, allows light to go through, it's called transparent. If you have a wall or a physical metal or something like that, don't allow light to go through, that's called opaque. Like the same thing for current, electricity. If something allows electricity to go through, it's called a conductor. An insulator is something that will not allow electricity to go through, right? It's transparent and opaque to electricity. So metals, acids, things like that are conductors. They allow electricity to go through. Wood, plastic, porcelain, ceramic, these are things that are insulators. That's why switches are made out of, they used to be made out of wood, then they bakelite, and now they're made out of plastic because they are insulators. They don't allow current to go through. So you know what a conductor is and what a insulator is. What is a semiconductor? A semiconductor is a somewhat strange device that allows current to flow, but only in one direction. It's something that we are not familiar with. So that's what it does. And now we have glasses like that, right? A glass that allows one-way glass. You can see through one way, but not the other. The semiconductor is something like that. So let me use a simple kludgy thing to show this. We all know how a battery works. A battery we have a small battery cell. We have this point, the tip thing is called positive, the flat end is called negative, two sides of electricity. You connect it to an electric light bulb, the bulb will glow. As long as its power is sufficient there, it will glow. If it is connected through a conductor, usually we use a metal wire, and now we just to avoid shock, we cover the metal wire in plastic plastic coating. So, wire will connect and the conductor will allow the current to go through. Or we can have an insulator. Suppose you put this through a block of wood, then what will happen? It doesn't matter that the metal is there in the other directions, the bulb will not glow. It's an insulator. There's a piece of wood in between, so it will not conduct electricity, so it won't go through. So it's as simple as that. So now it doesn't matter for a conductor or insulator whether you battery goes this way, battery goes that way, current goes this way, current goes that way. It doesn't matter. Conductor allows current, insulator doesn't allow current. So, but what is a semiconductor? It allows current only in one direction. So this black triangle here is a representation of something that I call a semiconductor. If I put this flat shape of this semiconductor, this point, if you connect inside that circuit, that's positive, and the sharp edge, the vertex, is the negative edge. So if you connect this thing in this direction, then the current from positive current, flow of current is like this, right? The positive current goes like this, and it completes the circuit, and this semiconductor will allow current in this direction. But if you flip this thing, the battery you keep the same, but if you flip this thing so that its negative point of the semiconductor faces the positive, receives current from the positive aspect of the battery, then it will not allow the current to go through and the bulb will not glow. So it's a conductor that allows current in one direction, but if you reverse it, it won't allow current to flow through. That's what a semiconductor is. Okay. The first real semiconductor that was discovered actually goes back a while, but the most famous one is the diode, a vacuum tube diode, and that came through an accidental invention. It actually goes back to Edison. Edison invented a light bulb, and we all know that the light bulb, electric light bulb Edison had, was a vacuum bulb. Even today we use these bulbs. The filament bulb is a vacuum bulb because you don't want the metal to interact with the oxygen, getting heated with the oxygen and become metal oxide. And when he did the vacuum thing, he found out that one part of the bulb, the glass, was getting darkened. He didn't know what that was. One of his researchers, assistants, William Hammer, found it, and they called it, today they call it thermionic emission, but Edison then patented it, and so it was called Edison effect in 1883. And they didn't know how to fix it. Edison said, put another metal, see if that works. And they did, and it prevented that glass burning, but they didn't know why it happened. They couldn't understand the physics of it. And it turned out it is because that hot filament inside the bulb is literally emitting electrons, and it's the electrons that are moving towards the positive side of the battery. But in this period, electrons are not known. They were only discovered in 1897 by a person called Thomson, and so we won't come to that. But after Thomson discovered electrons, literally he used a vacuum bulb like Edison set up, but he used something called a Crookes tube, which is a much larger version of the Edison tube, with a second larger plate. And that larger plate was given a positive charge. So these things were, flowing things were connecting. And so he realized that there was electricity going through the vacuum of the bulb and hitting the plate. So he tried to understand what it was. He found out they were electrons. Now, one of the persons who worked under Edison was this person, John Ambrose Fleming, the person in this picture. And in 1904, he realized that that second plate that you do that, if you connect it in a positive plate, a positive battery, a positive terminal of the battery to the second electrode, then the vacuum tube allows the current to flow through. But if you flip it around and connect it to the negative terminal of the battery, then it would not allow the current to flow through. So it was acting as a semiconductor. So the vacuum bulb with the second electrode was acting as a, so this it's not very clear in this. It's it's kind of a more sophisticated device, but there is a second conductor over there and a terminal for that. So you're seeing multiple terminal sticks coming out of this, and he effectively realized that by this time alternate current was used. So it would, for alternating current, it only allowed the positive current to go through and prevent the negative current from going through. So you could do what's called converting alternating current to direct current, that is eliminating the negative current, and that was called rectification. Converting alternating current to direct current is called rectification. You could also do that with radio currents and so on. And it could act as a radio detector. So this is something that multiple things it discovered. One is that it could be a diode, that is it could be a semiconductor. The other that it could be a radio detector. So those are two things that he discovered with it. So because he invented this diode, and the diode is kind of the first of the electronic devices, because this is the first device that worked using understanding of how electrons work. And you didn't, with all the electrical devices like a switch or a light bulb or a resistor or an insulator or a capacitor, you didn't really fully need a battery, etc. You didn't fully need to understand electrons. But with this diode, you really had to understand what an electron was. And so he's called the father of electronics. Couple of years later, this gentleman, Lee De Forest, introduced a third thing. You can see this thing that's rolled around this thing in a coil. He put a third filament into the diode. And with the third filament, you could supply current or increase or decrease the current on it, and that regulated how much current would flow across the other two electrodes of the current. In fact, this thing was called diode because there are two electrodes, and this thing was called triode because there were three electrodes. Now we found out that because you could use this third electrode, you could configure the triode to be a current amplifier. That is, if a current comes through, if a signal of a current comes through, you can actually amplify the signal and feed it to a separate circuit. So this is fantastic because you can take any electrical signal and make it a larger signal. And so this is kind of equivalent of it is kind of like the magnetic lens of electricity. And that's something that was very, very useful. So it's something that was an amplifier. So the triode really became the founding, along with the triode became the founding instrument of the modern electronics. And these two, the first application really was radio. Radio detectors had, people didn't know what to do with the radio, which had been discovered before. But Marconi in 1909, Fessenden in 1906, and others came up with radio devices, and they became very popular. And then Edison's gramophone, which he invented 20 years back, was not very popular because, or had limited popularity because it couldn't amplify very much. But now with an electrical amplifier, you can take the soft sound of the recording and amplify it with the large sound, and then the gramophone record and the gramophone player, all of that became very popular. Radio became very, very popular too. But these are not the first semiconductors invented. They were the first semiconductors for which practical use was actually discovered. We go to Michael Faraday, the person in this picture, to actually be, he gets credit for discovering the first semiconductor. And that was actually a very different device. It was something called a thermistor. He realized that he could pass current through something called silver sulfide. It's just a something, and that when he shone light on the silver sulfide, it conducted electricity better. This is very strange. He didn't think light should affect light or heat. Actually, it turned out to be heat. Heat was affecting the material. And that material was conducting better. Conductivity was actually increasing when you shone a light on it. Turned out it's not the light but the heat. When you remove the lamp, because the lamp had a heat on it, when you removed the lamp, it reduced its conductivity. So conductivity increases due to metals. Later on, they found out in some metals that it increased conductivity, and some other materials it decreased conductivity. So you had either a positive effect or a negative effect. It could increase or decrease. But this is actually, so this was called the thermistor, and that was kind of the first device that was discovered where you could, change the conductivity of a material based on incumbent heat. In 1874, nearly 40 years later, Ferdinand Braun, a German researcher, was experimenting with galena crystal. Galena is lead sulfide. This is silver sulfide. This is lead sulfide. And he had tinkering around with the metal wire. And it turned out that galena sulfide acted like a true diode. That is, it allowed current only in one direction, but would not allow current in another direction. So again, they didn't know what to use it for. They just discovered it theoretically, and they had no application for it. They didn't want a device where it would allow current in one direction. And it was of no practical use until radios came along, and then it became popular. This man also invented, just as an aside, he also invented the oscilloscope, and he was given the Nobel Prize in 1909. He actually shared it with Marconi. So this other semiconductors were already in place, And then our Indian fellow comes along, Jagdish Chandra Bose, Acharya Jagdish Chandra Bose, after whom this major road is named in Calcutta, as one of the most respected people in Bengal and one of the great scholars of Indian science. He was also tinkering out of this lead sulfide crystal, galena crystal, and he realized he could make a detect millimeter radio waves with it, and so he filed a patent for it. In the US, he filed a patent for it in the US, and that was given, and that became, a potential contact, component of a radio. Of course, radio would pick up only much later, but at that point, it was a scientific curiosity, so they were using it to detect radio waves. But in a very few years, another person called Greenleaf Picard experimented with silicon crystals. Now, this is silicon rather than lead sulfide, and discovered that that would do work, detect the stuff. And then he came up with something called cat's whisker radio detectors. And then other people around the world started experimenting, and they're doing stuff. There's a person called Michi Torikata in Japan. There is Oleg Lasov in Russia. He came up with some carborundum as crystal detectors. So they were using not vacuum tube detectors, but crystal detectors. Remember, these are the major application here was for detecting radio waves. So radio was a more popular device. They were still not being used for switches or stuff like that, but that was a very popular device. So they were doing this. But they found out that the quality of vacuum tube, because people are doing researches on diodes and triodes, vacuum tubes are actually much better. They handle higher voltage much better. They're easy to make. We had several years of making glass and filaments, and Edison was making, the companies were making light bulbs for like a long time in large numbers. So what happens is crystal detectors lost their importance or their utility, and vacuum tube diodes became more reliable, and they were popular for after a few years. So they became popular. Along went a few years later, the concept of a semiconductor was finally explained by Walter Schottky. The physics of what this thing is was explained by Schottky. By this time, atomic physics had developed, chemistry had developed, people had much better, by this, in this early period of Bose and all that, they didn't even have the atomic model. Rutherford hadn't done this experiment. Bohr didn't know, hadn't come up with the hydrogen model. We only had electrons, and they barely discovered protons. They're still to discover neutrons. They didn't know what an atom was. They didn't know if atoms existed. And Einstein proved it later on, and so on. And so, in a few years, what happened? Physics advanced, and they had a lot of interesting concepts that they understood. What electrons were doing, how atoms were exchanging electrons, how radio was being passed, and so on and so forth. So a lot of this thing became very popular, and he explained semiconductors, and they were used very extensively in radars in World War II, and they are making silicon and germanium things, and they were very useful, it turns out. So not vacuum tubes, but silicon and germanium semiconductors are being used to detect electromagnetic radio waves. Notice that all this time these things are only being used as radio detectors. That is the primary use for them. In 1940, a person called Russell Ohl discovered a completely new concept. What he did was added what is called positive and negative impurities to silicon and germanium. Silicon and germanium are the famous semiconductor materials. And what is the adding an impurity? I will explain this a little later. And when he did that, if you add basically he was just what's called doping it. He's adding a few impurities. He's using either phosphorus or boron. Depending on which you added, it will become little more positive or little more negative. And so that doping turned out to be a very powerful effect for this, because now you could take phosphorus doped silicon and a boron doped silicon, put them together, and they would actually act as a semiconductor diode. Instead of using a vacuum tube diode, you could have a semiconductor diode. The advantage of semiconductor diode is much smaller. So by this time, millions of silicon and germanium crystals are being made because they are popular as radio detectors. There's MIT Radiation Lab that's doing detecting them, University of Pennsylvania. So it's not just companies that are doing it. Universities are manufacturing crystals at their laboratories in large numbers. So this became very popular, and so the atmosphere was ripe for doing experiments with this, adding impurities and so on. So after a 20-year gap where people are going back to vacuum tubes, semiconductors like silicon and germanium came back into fashion. At this point, what happened was, based on this semiconductor diode, three people in Bell Labs, that is Bell Labs is founded by Alexander Graham Bell. It's part of the company that founded American Telephone and Telegraph. It's primarily a telephone company that had a fantastic research laboratory. Three people called John Bardeen, Walter Bratton, and William Shockley developed something called a point contact transistor. For this they won the Nobel Prize. And the year after that, Shockley went along and invented something called the junction transistor. So this is the first transistor, electronic transistor, which became, it was named that because, the way it worked, it was apparently doing what's called a transfer of a resistance. So the name transfer resistor was combined to make it called a transistor. So this thing also acted as an amplifier. Remember the triode that could be used as an amplifier for electricity? This transistor now is something that was a second electronic device that could be used as an amplifier. And that is literally what they were going for. They are taking the P and N impurities of a junction diode, wondering if you could make a PNP or an NPN thing and make a transistor out of it. And they actually succeeded in doing that. So Shockley managed to do that not with the point contact transistor, but with the junction transistor. And literally most of the transistors that today you use are a junction transistor. This is a very unwieldy device, but this is the first device that kind of showed this. And they got the Nobel Prize for this in 1956. So the other importance of this is that now you had a solid state, that is a crystal-based diode and a crystal-based transistor, both a semiconductor and an amplifier. And so Bell Labs didn't know what to do with it. So what they did was they licensed the technology. So anybody else could manufacture that and start using it and selling it, as long as they paid Bell Labs a fee. So probably they could have become the critical factor in doing this. And so this is what the first transistor looked like. And the transistor is the fundamental component of today of all electronic computers. And this is what it looked like, right? This is what's called the P portion, the N portion, and then there's the other one and so on. It's very bizarre looking thing. Of course, this for electronics engineers, this is a very key thing. For computer engineers, 1947 is the famous year of the transistor. But we, of course, think of it as a different thing for India's independence. So we'll move on. So this is what a junction diode looks like. This basic thing is P or N is basically silicon or germanium, basic semiconductor. You add phosphorus or boron to it, it becomes active. It becomes more positive or more negative. And if it is positive negative, what happens is you can use it as a diode. So it will allow current if its positive terminal is connected here and negative terminal is connected here, but it won't allow current the other way. So it acted as a proper diode or a proper rectifier. The junction transistor that Shockley came up with, simply like this two diodes put together, but it's actually a thin intermediate layer. You could have two positives on the two sides and one negative thin layer, or you could have two negatives on each side and put a positive one. So this is a device, an electrical device with 3 LEDs, not 2 LEDs. And this is a way to do some things. And this turns out electronically to be very useful to store data, to be an amplifier, and effectively be an important concept of a logic gate. You can build a logic gate, an AND gate, an OR gate, or a NOT gate with a transistor. Just like you could build one with a triode and a combination of other circuits. And so this led to development of several products after that. You can see here, these two are little transistors here. These are 2 vacuum tubes. So this one actually, these are 2 vacuum tubes and a transistor. Okay. So this is the first device that was used with the transistor. It is a sonotone hearing aid. It's a large device, the size of a smartphone today. And this was manufactured by the Sonotone company. It had 1 transistor, 2 vacuum tubes. It cost about $229. We have the exact details. A couple of years later, another company called Raytheon came up with the similar hearing aid, except it used only transistors and skipped the vacuum tubes. And Raytheon licensed technology from Bell. All of these companies are basically licensing technology, transistor making technology from Bell. And after that, they never started, look back. Transistor component became very component to the vacuum tube radios. The radios before this were mostly made with triodes and diodes, companies started making them with transistors instead. So in 1953, a company called Intermetal in Germany made transistor radio. Regency and another company called Texas Instruments started making them in 1954. They were selling 100,000 units each at $50. So look at this, 52 to 54, from hearing aid to radio, we went from $200, $300 to $50. Then another Japanese company called Tokyo Communications Company tried to do the same thing. And this is the company that later became Sony. They changed their name because Tokyo Communications Company was a handful or a mouthful, and Sony was a good brand name change. And then another company called they made the transistor radio for about $30. So from $50 to $30 just in 1 year. You can see this trend in electronics that the more time passes, the cost of the components lowers, and so the device actually reduces. We always talk about inflation. We never celebrate deflation in electronics or computing goods or mechanical devices and so on. That's actually a very important phenomena that we see in our economy. The world is much richer because of the dramatic reduction in costs that brought by electronics, with corresponding increases in productivity and ability. So they're making silicon and germanium, but the material science work of silicon was difficult. So people are using germanium. Germanium is actually not that conducive a thing because it has a limited temperature range. It only 0 to 70 degrees Fahrenheit. Whereas silicon had a much better Fahrenheit temperature range, minus 55 degrees to 125 degrees. So you could operate it in much greater environments. It would be a reliable device. It could, if you could make silicon transistors. So Bell Labs took the transistor to the next level, and they made a fully silicon transistor, not germanium, but a silicon transistor, headed by a team called by Morris Tannenbaum. But they didn't pursue it. They did the research, they published it, and then they were very happy to license the thing. And one of the people inside the team called Gordon Teal left Bell Labs, and he joined another company called Texas Instruments. And he went there, and Texas Instruments, quickly using this technology of silicon, dominated the transistor market. They famously made this thing where they showed this transistor compared to the very small postage stamp. It is like 1/6 of the size of a postage stamp. So look at what a small device it is, whereas a vacuum bulb can be much bigger, like the size of an electric bulb. So this is a very, the transistors became very popular. A lot of electronic devices, primarily radio, but at the time television also to come through, and other electronic devices. People are inventing electronic devices. We'll come to computers shortly. At this point, we had the advent of a completely different technology from photography and chemistry. From photography, we had a capacity of making masks. You know that photographs are using a negative, and you can create a positive print based on negative and so on. So you can the negative acts as a mask, and then using a chemical emulsion, you make a hard print of it, hard print of the actual photo you want. That concept of a photo mask was combined with certain chemical understanding of how silicon could be processed. You take this is a very beautiful example that I took from the internet. You take a metal substrate, you have a substrate, you put some metal on it, you add something called photoresist to it, right? And over the photoresist, you put a photo mask, and then you put, you bombard it with light, you expose it to light. What happens is that photoresist goes away, leaves this part of the metal away, and then the rest of it, goes away. So you can see this is what happens. That light going through that photo mask leaves this part and erodes the remaining part, right? This is called, and this part can be taken, and just this part of the metal can be left alone in that substrate. So you can, make a mask and literally sculpt a circuit on the underlying substrate, right? That's what you can do. You are literally using photography and chemical coatings to write, really etch a circuit. You can etch circuits on a substrate using photography. So this is this is positive. The other opposite is negative, where it covers the where it burns away the photoresist and leaves the other part. So whichever one is convenient, you can use. And this turned out to be great, a very important concept, because you could make a very complicated mask of an electronic circuit, and the mask, and then you put this photoresist and all that. And what will happen is you can focus that using a lens, and it can take this pattern of etching and eroding and all that stuff, and create that pattern on a silicon wafer. This thing here is a silicon wafer. This is your lens, and then this is your mask, and then the light coming through the mask go through this, focuses on this particular part. So the same pattern can be repeated again and again about 100 times. So once you design the circuit, so basically once you design the mask, you can create an electronic circuit simply by creating this mask and applying photoresist and literally photolithography. Photo, of course, is light. Litho is stone. Lithography is stone writing. Like people, write on stone using hammer and chisel. Except here you're using light to etch on a silicon wafer. That's literally what it is. This process really made miniaturization of circuits very powerful. Now, Silicon Valley is called Silicon Valley because Bell Labs managed to get silicon to work better than germanium, and because Texas Instruments then ran away with the technology and made like lots and lots of these components, and the electronics industry really took it up. Now, Shockley, who had invented the PNP junction transistor, decided to leave Bell Labs and go form his own company in California. And he went to Mountain View. In fact, not very far from where in fact, that's where the Computer History Museum is also there. And he founded a company called Shockley Semiconductor. And with him went some of the great names of the field of computing: Gordon Moore, Robert Noyce, Gene Horney, and all these guys. Strangely, instead of focusing on the transistors, Shockley decided to work on a device called the PNPN diode. Don't worry about what it is. And it had an application mainly in telephony. And because he came from a telephone company, I thought perhaps he thought that was where the great market lay. So he tried it. But what happened was several of his employees decided that that's not where the future was, that the transistors were where the future was. And so they left Shockley and formed their own company called Fairchild Semiconductor. These are the 8 people in the photograph. And these became notorious as the Fairchild Semiconductor Group. Shockley never forgave them. He called them the traitorous 8 and so on. And they moved to neighboring area, Palo Alto, which is like a couple of miles away from Mountain View, down the road. Actually, it's not very far away from there now. And he went there. These guys went there and decided to start a company there. This is a photograph of the Fairchild Semiconductor Group and their notebooks and all that. And this is from the display at the museum. They even displayed their notebooks that the Fairchild Semiconductor research team used. They used a lot of these notebooks to communicate and come up with devices, studied a lot of these properties of transistors and semiconductors. And they came up with something else called a planar process. A planar process is one where all multiple electronic devices can be etched on a single surface. So multiple transistors can be put on, multiple diodes and transistors, instead of putting 1, 2 and all the connecting the transistors as making each transistor, connecting them externally by wire. You could connect all put a bunch of transistors on one single silicon wafer and connect them using some wire. And so that was discovered, and that really made a huge difference. At this point, IBM, the computing company, decided to use transistors for their computers rather than vacuum tubes. Remember the computers that were made with ENIAC and all that using vacuum tubes? They had the computers went from vacuum tubes to using silicon transistors because transistors are much more convenient and easier to wire. So IBM wanted to make a transistor, computer, and ordered 100 transistors for $150 each. One transistor costs $150 each. Now, this phone has like 1 billion transistors, and this phone is probably less than $150. That's where it started. And they're split into 2 teams. John Horney this is John Horney, and he led the team, the PNP transistor. Gordon Moore led the team with the NPN transistor. They found out that the NPN transistor actually worked better. They had some reliability problems that they worked it out. And John Horney famously said of the planar process that it is the most important innovation in semiconductor industry because you could put multiple transistors on the same surface. What did that lead to? It led to the integrated circuit. Integrated circuit was more than just putting multiple transistors on a circuit. You could put multiple other electronic components also on a single chip, and this was discovered or patented by a guy called, or tried to patent by a guy called Jack Kilby. He's a researcher at Texas Instruments. In 1958, he said you could put multiple components on a single chip. You could put transistors, you could put capacitors, you could put resistors, and he came up with what's called the first binary flip-flop circuit. A flip-flop is literally a digit store, a device that stores one digit. You can feed it, you can send a circuit, it will say whether it's stored a 1 or a 0, and that flip-flop costs $450. But the wire connections are not available, were not viable. Along came another researcher, Robert Noyce, and he came up with this. The other person who came up with the integrated. In fact, the integrated circuit, the credit is given for both of them, both Kilby and Noyce. They were honored by the computing industry. They were honored by the electrical industry, electronic industry, and they are given joint credit for coming up with the integrated circuit in two different fashions. This is what Kilby's chip looked like. It's a one messy thing. That's what happens when you're working in a laboratory. It doesn't look anything like an integrated circuit. From there, we went to this. So once you started putting multiple components on it, in the 1950s, they put one transistor on a silicon chip. In 1960s, a couple of years after this Kilby's chip and Noyce's devices, they managed to put 16 transistors on one thing, and it was a 4-gate thing. By 1970s, they could put 4,500 transistors, and that was an entire control unit of a computer by itself. Okay, that was an entire control unit of a computer by itself. So that became called a processor. So it became not a control unit, logic unit, math unit, all these different circuits that are part of the computer, but one single chip could do multiple things. So they call that a processor, a microprocessor. And then from there we went to 32-bit, the photographic technology, the etching technology, the transistor, everything got better and better. The things were connected with gold wires because gold is one of the thinnest things. All these things have gold wires. So from the 80s, we went to 32-bit microprocessors with 275,000 transistors. In the 90s, we had 3 million. In 2000s, we had nearly 1 billion. And 2010, we have 8 billion transistors on a single chip. Went from one transistor to 16 transistors to 8 billion transistors, roughly on this, the chip is the size of a fingernail, right? It's a tiny thing. They can put 8 billion electronic components on it. It's just completely astounding what they are able to do. And this is entirely because of electronics. You can't do this with mechanical engineering, or you cannot do this with electromechanical devices. You had to do electronics to do this. And you could not just do it with transistors and diodes. You had to do it only with you can only do it with integrated circuits. And for that, the planar process, the concept of photography, photolithography, and being able to etch not only multiple transistors, but multiple components of a chip were fundamentally essential. So the criticality of electronics, the criticality of planar process and silicon to integrated circuits, and therefore the massive increase in power and capacity of the computers are a major factor. Besides this, they are also making other devices. Once the computer devices, so the chips, the control unit, the memory unit, the processing unit, they were all making electronic chips. But external memory or outside storage tank, they were also experimenting with technologies there. They had the mercury memory tank, you had memory tubes, you had drums memory, you had core rope memory. I won't explain this, it's just very interesting. One of the Apollo rockets actually had core rope memory. Different types of storage, mostly magnetic storage. It's not electric storage, but it is magnetic storage. Magnetizing certain coils. Even today, most of our hard disks all use magnetic storage. Only our CDs and DVDs used optical storage. They store, data as pits or flat surfaces, and a laser reads them as a pit or not a flat surface. Then we had from drums, we went to tapes, and from the tapes, we went to literally cassette tapes, right? They evolved around those things. The audio cassette tapes evolved into the computer cassette tape, large tapes to store data, store memory. And then they came up with the concept of a disk memory, like a magnetic disk, like a gramophone disk. So the disks are using magnetic storage also. These are the other devices that came. So additional devices outside to store the programs and all that. So if you to trace the electronics history of computers, you have to look at the development from the diode, from Fleming, triode, Lee de Forest, the concept of silicon germanium diode, visioned by Russell, and I'm leaving out Schottky and all the others, point contact transistor, then the junction transistor, then the understanding of working, silicon better than germanium, the invention of the photolithography process, coming up with the planar process, and then in developing the integrated circuit, and then going on to the very, very complicated integrated circuits. This is this is the development of the electronics part of the processing of the computer, process of the computers. So computers are categorized based on what fundamental components that they had as 4 generations. The first generation computers used vacuum tubes. The second generations, actually there was a stage where some computers used both vacuum tubes and transistors, but second generation mainly used transistors. The third generation started using the integrated circuits, and fourth generation used all kinds of integrated circuits: small scale, medium scale, large scale, very large scale. Really large scale and very large scale is what you really should call fourth generation. And this actually had an effect on the size and the cost of the computers. The first 2 generations were what they are called mainframe. By the time integrated circuits, we could shrink the computer to much smaller sizes, and we had what are called mini computers. And when you had large scale integrated circuits and microprocessors, you could come up with a computer that could literally sit on a desk, and then you could have something that could carry on a lap. And today, of course, you can carry one on your palm, right? This is a palm top computer. You call it a phone, but it's really a palm top computer. So you look at, I've summarized kind of the development of the computer from electromechanical to electrical, because the mechanical and the human computers really don't fit into the kind of automation you're looking about. You had Zusa in 1941 with relays, with Colossus with 2,500 vacuum tubes. That also has used relays. Actually, Mark I used relays. The ENIAC used vacuum tubes. This Madida used vacuum tubes and diodes. Then Uniac, even after that, people are using vacuum tubes. There's a computer called Sage in 1958, which used vacuum tubes, diodes, transistors, a bit of everything. And in 1961, IBM came up with something called the 1401 computer, which used entirely transistors. 66, even their computers started making, started using integrated circuit rather than transistors. Hewlett Packard and others started making interesting, then mini computers came along. You look at the cost of these computers. In the 1950s, Remington Rand, Univac, the computers are literally $1 million. Each computer was $1 million. They sold 19 computers that year. Okay. IBM had a model called 701 1954. They developed a rental model for a computer. $1 million is too much for a computer. We let you rent a computer, and you could literally rent it for $15,000 a month. Then the Digital Equipment Corporation came up. Once the integrated circuit transistors and all that came along, they came up with the mini computer. They came up with a computer called the PDP-1, and this was priced at 1/10 of the price of the mainframe computer. That's why smaller companies could start affording them. And once that happened, a lot of people started developing computing devices. IBM itself started coming up with smaller devices, though the mainframes are still in demand for very large applications. They invested $5 billion in the development of the system. That became a very popular system. It's still in use in some places. A lot of these computers are not gone, they're not gone out of operation. They're still, some of these computers are still working somewhere or the other. And then Digital Equipment Computer came up with from 90,000, they went to 100,000, they went to 18,000. Data General went down to 8,000. And by the 1970s, with microprocessors, a company called MITS came up with a computer called Altair. This is famous because they developed the computer, but they developed an operating system. They sent out a message, put an advertisement in the paper for somebody to write an operating system. And a Harvard student called Bill Gates, along with his friend Paul Allen, wrote an operating system and went there. And then he started a company for it, and that's how Microsoft formed. And then meanwhile, Jobs, Wozniak, and a couple of other came up with a computer. They developed a computer and came up with a computer for less than $1,500. In 1980s, an Englishman called Sinclair actually came up with the Sinclair Spectrum ZX computer. This was literally priced at £100 or $150. So he went from $1 million to $100 in barely 30 years, right? When you look at it, this is where the computers got categorized. This our Spectrum 1G, 2G, all computers comes from this computer technology really. You look at the size of the computers. First generation computers and second generation are mainframes, third generations are minis, fourth generations are laptops, and these are the components, right? The triode, the planar transistor, the integrated circuit, and the very large scale integrated circuit. These use those things. You had the semiconductor numbers. You had 18,000 on this, 50,000 here. You had 200,000 transistors on this this computer. The chip itself didn't have that many, but the computer had a lot. Today, one chip can have 8 billion transistors or more. The computers went from room-size mainframe computers to smaller size and fridge bureau size, and then now they, microprocessors. You can have them on the desk or your palm. Calculations per second. They use something called floating point operation per second. This is how many numbers you can add together in 1 second. The early computers, this period they were not even calculating, they're not even keeping track of it too much. This in the 50s and the 60s, they could do about 10,000 to 100,000 calculations per second. That went from 1 million to 100 million calculations per second because the computing power of the speed of the computers, the power of the computers, all of that dramatically increased. And today we can do, from the 80s to today, we went from 100 million to 100 billion calculations per second. So mind-boggling speeds, right? And the cost of them went from $1 million to 100,000 to 20,000 to 2,000. Today, of course, the computers are, you can get for $400, $500, you can get a fantastic computer worth a lot. You can, even lower computers are there. Of course, or palm-top smartphones, you can get, $100 to $100 is like what, 70,000? For $50, like 40,000, 35,000, you get excellent phones, right? $15,000, you get 15,000 rupees, you have a phone. It's very cheap. The user base, the first computers had very few, not many people could spend $1 million to buy a computer. It increased. Today, of course, 1 billion people use the computers. So the computers' performance and cost, the size has gone down, the cost has gone down, the performance has gone phenomenally huge. This is what an IBM 1400 mainframe looked like. That whole thing is the computer, right? It's all different components. It wasn't very powerful. This phone, the laptop that you're seeing it on the phone, it is seeing is more powerful than this computer of that day. In terms of computing processing power, of course, it had more input-output capacity. This is the digital mini computer. You can see it went from room size. This is like half the room, right? It went from, honestly, a very large room too. From half a room to something the size of your closet or fridge, a couple of fridges side by side, or even a large fridge. This is a digital equipment computer. And from the 90s, we had personal computers that you could use on your desktop. You have a laptop. I'm giving this talk on a laptop. Basically it's sitting on my desk. And of course, you have smartphones today. This was something that was said in the 1990s. If a car performed like computers or could progress like that, it could give 50,000 kilometers of mileage per 1 liter of petrol. Engine would be milliliters rather than 2 liters, 3 liter engines, and it could run not just a car but an entire aircraft carrier. Think about 8 billion operations, and it would cost only $5. This is a joke that was made, and this is a joke that was made in 1990s. Today, of course, it is probably more true than ever. This thing now, because of its computing not just computing capacity, but also its communications capacity, it brings you the whole world at your fingertips, literally. So absolute amazing development in the field. Now, I have focused primarily on the early stages of the computers and about the electronics of computers. There is a whole other aspect to it. There are multiple other aspects to it. I mean, I flipped through even the electronics just to give you the major stages of it. Each stage, of course, had very interesting stories. People, of course, study, an entire 4-year course for this. Perhaps you can do graduate courses and all that. The other aspect of computers is something called software. I'm only going to briefly touch it because that's too complicated to, it will take a separate set of lectures which I won't go into. Early computers are used in written programs called machine language. Then they went to assembler, and then there is something called Fortran that came along. To cut a long story short, first computer had no memory, no software. EDWAC had a stored program, and the stored program literally had data like this. This is operation, operand 2, all written binary numbers, right? This may make no sense to you, but literally these are standing for this equivalent stuff. This code 100000101 stands for add, and this thing stands for this number, fetch this data from this, this particular point. This say fetch this data from this point, jump to this particular point. So series of codes that are stored in the memory stand for things. And this is too complicated for most people. So people started developing something called assembly language. This is assembly language. It would literally have instructions literally like this. People said at that point, a very strange statement by von Neumann. He said, no computer is likely to need a program longer than 1,000 lines of code. The great geniuses had no idea what computers would evolve into, what it would, expand into, and so on. Very famously, John Watson, one of the big CEOs of IBM, when they first made the computer, apparently famously said, I don't see, who would buy a computer. Maybe 5 or 6 people would buy a computer. Rather than that, I don't see a market for it. And Bill Gates is famous for having said 640 kilobytes should be enough memory and so on. So people had no idea what this is. And he also said, why do you need anything but assembly language? Being a mathematician, von Neumann would say that. But in 1953, IBM developed a team under John Backus, and he said, engineers are spending more time configuring the computer and not solving the engineering problems. We need a program that can translate mathematical programs into assembly language. So instead of doing all that, writing that assembly language programming, you should be able to express it in a higher level format, and the computer should do it for you, because after all, it's a data processing device. So they came up with some computing language called Fortran, Formula Translator. And it took 4 years for them to develop, and they developed it. And once that came along, very few people start doing work in lower level languages. Along came COBOL, that Grace Hopper actually headed the team who came up with the language, language for business programming. Then came another language called ALGOL for algorithmic logic, a language called Pascal, named after the famous inventor of the Pascaline adder. A person called John McCarthy came up with a very different style of programming called Lisp, stood for Lisp processor. Then there is BASIC, C, C++, now today Java, Python, all kinds of other computing languages are coming along. So this is a very interesting development. I have not talked about the software part of it at all. It's a very interesting aspect. But I just want to give a narration of how clueless they were in the early part of the software industry. This is an interview by a lady called Jean Samet, who was looking for a job. She's a mathematics graduate, and she was interviewed by a person called Arthur Hauser, who was working for this company, and he was hiring. Okay, he's hiring. The interview doesn't even look like an interview. Hauser just offers us a job and says, do you want to be a programmer? She said, what is that? What is a programmer? And Hauser says, something to do with computers. He doesn't know what it is. He's hiring a person. She doesn't know what the job is. He doesn't know what it is either. And so she kindly asks him, is it like using punch cards? He says, yeah, I think so. Yeah. And she says, oh, I can do that. And she says, oh, congratulations. You're now a computer programmer. I don't think any programmer today can have an interview like this. They torture you with all kinds of fascinating questions. But that's literally how it started. Mathematicians trying to do some stuff, simple processing, something to do with punch cards. They were hired and, went on to be programmers. And they developed programming, and it became, now it's like a gigantic industry, right? One of the largest industries in the world. So in this PowerPoint, we focus on the development of electronics as the driving force, because that is the part I wanted to talk about. We think of all other electronic devices, but I think this is a particularly interesting one. But some developments in several fields helped in this invention, evolution, which is why that court judgment is perfectly correct. No single individual can really get credit for inventing the computer. You had inventions in material science, the understanding of semiconductors, doping, photography, films, emulsions, and so on. A lot of chemistry there. Mathematics, Boolean algebra, binary mathematics, linguistics, Turing machine, information theory. Don't worry if you don't know what this is. I'm just giving you certain information that such things exist. In physics, you had electricity, the development of electromagnetism, the discovery of electrons, to understand even how electronic devices work, to understand how atomic physics worked and how silicon works. Chemistry and then bond structure. You need markets. You needed buyers for computers that were very demanding in terms of computing processing. They were really driving the invention of the technology. The Census Bureau, as we saw, tax departments, payroll departments of large companies, airline companies which wanted these things for their reservations, telephone companies, banks, all of them, large companies, all of them multinational companies. At that point, there are not too many multinationals. Today, of course, there are a lot of them, and even the smaller companies are very, very complicated, computing demands. So all of them drove the device. In the 70s in India and a lot of the countries, there was actually a lot of labor unrest. People were terrified of computers. People thought everybody would be, replaced by computers. Machines would replace people. Computers would. Now everybody has several computers at home and several computers at work. And then military demands are another driving force. Encryptions, missiles, trajectories. These are the early driving forces of the first computers, as we saw in the case of Colossus, Mark I, and all that stuff. Conrad Zeuss's computer also. And then, of course, the field of software, where we went from assembly language to high-level languages, compilers, operating systems, and now there is a plethora of app developers and all that. So that's kind of an overview of the various aspects of computers. You could compare the invention of the computer with the invention of the electric light and say, who invented the electric light? And you could say Edison and say no, but all of these things had to come through. You had to understand magnets, transparent glass, pumps to this thing, steam engine to generate electricity, batteries, understanding incandescence, electricity principles, all of that combined to make the light bulb. Like that, you had mathematics, you had electricity, algebra, photography, chemistry, diodes, triodes, information theory, photolithography. All of this had to come through to several other ideas, software, and all of this to come through to drive the invention of the computer. And so the photos I used, of course, are photos I took from when I visited the Computer History Museum. If you go to California, I strongly suggest you go there. It's a very nice museum. They have a fantastic website. So if you're not going to California, you're sitting at home, go to search for Computer History Museum. They have a wonderful website. Some of the information about like Russell, some of the information I knew because I studied in computer science and all that. But I've never heard of Russell Lowell or George Tibbets and all that. So that was very interesting information. There's a book on computing programming languages by a New York Times person called Gopu. That's also very interesting. Wikipedia and other web pages can also be relied on for very interesting information. So but they do have a lot of conflict information. So you have to be careful. And of course, my personal experience a few years in the industry and my interest in this field. So thank you very much for listening patiently to this talk. I hope it has been informative. I hope it has been interesting. In the last few years, I've had the opportunity to talk about a lot of subjects, but it's the first time I've talked about computers in a general forum. So I want to thank my other fellow organizers of the Varamira Science Forum for allowing me to choose this topic and presenting it. And thank you all for listening to this talk. Thank you.
Gopu, thank you so much for this entertaining and comprehensive talk. I have been working in the software industry for close to 25 years now, and a part of it is a little bit is known to me. But what you showed is in this last 1 hour or a little bit more than an hour is, I think, is a broad roadmap of what has happened, and I can see that there is a lot more scope for multiple lectures there.
Yeah. You remember we had Kathy talk about physics, and
Yes.
her YouTube has so many lectures on physics.
Yeah.
Right. So computer science, probably there's quite a few talks you can give. The history of computers are as interesting. In fact, probably a lot more people would be interested in computers than physics because you need a lot of mathematical understanding and scientific background. Here you can just kind of cruise along and figure it out. So yeah, probably
already I see one request for a talk about the storage technologies. I think maybe we will discuss it, and we will see how to do that. But there is a request for a talk on storage technologies.
Okay, we can get somebody. I just gave it. We can get somebody else to do it probably also. Yeah, sure.
So so my question is, you started way back with this baked clay to silicon, right? So you mentioned in the passing about abacus, right? So even today we look at people using abacus to do fast calculations.
Yeah.
How is it that we don't hear too much about it, at least in the till the 1800s or something, about abacus used for even accounting or those kind of things, purposes that you mentioned, the other mechanical devices by Pascal or others, right? So is it because this science is more West focused, or am I missing something there?
No, I think it's China, right? It's the abacus was confined to China.
Yeah.
And it didn't come to India or the West. It's except as a toy kind of a thing.
Okay.
By the time, so you look at other devices that came from China, gunpowder or compass or something like that, or paper making. They had critical utilities. For some reason, India, for example, we used seashells. I don't know if you know this, but a lot of people used seashells. The chodin solluvolla.
Yes.
So they were just using those, whatever was convenient, right? They didn't make this framed thing with beads. They were using seashells to do a lot of calculations. Apparently, they are plentiful. You lose them, you can just get them again. People use that. We all use still fingers, right? We are still doing. Children keep 3 in the mind, 4 in the hand, and all that stuff.
Yes.
So probably that kind of stuff. And abacus requires a certain, after a particular point, it requires certain utility.
Okay.
And I don't know if abacus, I have never used an abacus. I never learned how to do it. But does abacus include a zero? I don't think it has a zero in it. So our math is all zero oriented. So that might be another factor. I'm sure it's very useful for a lot of things, and the Chinese will use it. But that may be a factor there. I don't know.
Because the reason I asked this question is, as you mentioned, paper or gunpowder has come out of China and it is widely used, but unfortunately, this doesn't seem to be the case. So, my other question, I have a series of questions myself, and there are also some questions in the chat box. Okay. So, machine can do logic with electricity, right? So this seems to be a very important, a major a giant leap, if I can call that. Is it one single person or a group of people who came up with this idea, or is it a gradual one, and at some point someone realized that, okay, this is possible?
Which one?
Machines can do logic with electricity, right? So who came up with this? Who came up with this idea, or is it a group or one person? Or
I don't think it is any individual. I think we don't have a pinpoint where somebody went sat in the lab and said, aha, we can do this. Because you look at it, the punch card hollering is literally a mechanical device, right? So they were doing it. Babbage was trying to do things with levers. He was trying to do math with levers.
Yeah.
Right. We've had this mechanical adding machines and all that stuff. People have had them. Pascal and Adder is one of those things, I think.
Yes.
Tooth wheels and all that. India, we didn't try those. The Europeans tried some of these things.
Yeah.
Electricity, I think, with what do you call it? Electromechanical relays. The concept of understanding binary mathematics and combining it. They probably thought we could do some math with it. I don't know of any particular individual or a particular person that says, and I have not. The studies I have done, I never come across that said that you could use this. George Boole is one of those fascinating persons.
Okay.
Came up with the binary math.
Okay.
And that it wasn't very used for many fields, and then with computers it's almost tailor-made for them. So.
But this from what I understood from your talk, this particular step seems to be a important leap, right? So so that is why I asked. Sometimes things happen in a gradual manner. So one fine day you build upon something and you come up with something spectacular. So,
right. Good point. We don't know. I'm not sure who came up with that particular concept that you could represent numbers with this thing. Like I said, probably just a very casual thing that they did, right? People were playing with electronics for a while, and so.
And before I go to the questions, in the chat box, there are a couple of questions. How much did the war play in this evolution? Did it expedite it? Because I see that a lot of things are kind of ambling along. If I till 1900s, right? Even 1890, someone said that there won't be much in physics to study about. You can actually be studying something else, right? So then from 1900 onwards, it is like you are galloping, right? And the first 50 years, you see so much.
I think Kelvin said that. But yeah, so no, war is a driving force, but it's not the only driving force, and it's not always a positive driving force.
Yeah.
You are looking at, the Colossus or something like that was developed, because of the demand of war. But what if, Europe did not go to war? What if Conrad Zuse he didn't start because of the war, right? He was doing it independently. Maybe Germany would have taken that device in a different direction. We have no idea, right? Second, if you look at the internet was funded by America's Defense Department. DARPA is the first founder of the internet. But the driving demand didn't come from, the take-up didn't come up because of the DARPA. Only the early research kind of came of that. Even in American devices, all the technologies that they were sponsoring, the American military was definitely one of the major funders of technology, computing technology. They needed all these processors and all that stuff. They were calculating, they needed these things for fast calculations of missile paths, jet propulsion, fuel ratio, all these things, right? All the calculus problems and mathematical problems, they were coming out, they wanted devices for that. But it took off not because of that. The general public doesn't buy missiles.
Yes.
The general public does buy computers, right? Companies want computers. The general public has computers because companies bought computers, and companies bought them in such large numbers. People started using them too, and so that's kind of it's their thing that drives companies and business needs. That's really driving all of that. The fact that it can be used by us also. For example, none of us buy an adding machine or a Xerox machine for home. Most of us don't need one. Right? But a computer is so how should I put it? Multifunctional. So it's become an indispensable thing. In modern usage, I would say the phone is driven it, right? Because the phone became the computer. The number of smartphones far outsold the number of PCs, right? Because the market for that is different. So,
So to say is tell people how far we have come. Today, the smartphone I have in my hand has got more computing power than what was used to launch man to the moon. Is what I have. I have read. So we have come that far, right? So and it's maybe what 50 years.
Not one computer. Your phone is probably more powerful than all the computers NASA had or Russians had, right? Combined.
Yes.
Effectively computing power. Whether they actually do the stuff, it's a different thing. But pure computing power and cost and all that, it's gigantic.
So the side effects, okay, or the desirable consequences of this. You mentioned about the cost going down and the areas in which it has impacted. Once upon a time, a phone was with only a few people, and today everyone has a phone and they are using it for so many good things, right? Today digital payments won't be possible without everyone carrying a smartphone or a phone, and you are using it for so many good things, right? All these good things wouldn't have, maybe the people didn't think about it when they went on to build a computer, but all
nobody does. Nobody does. That's what I'm saying. I mean, look at John Fon, one of the most brilliant human beings. He says, "Why would you need anything other than assembly language?"
Yes.
So you can't see past a particular thing, and the collective brain of human race is far more than any individual. Even a group of very smart individuals compare nowhere to the collective brain, intellectual power of human society.
So that way, I think we need to thank all these people who have brought us here, right? Even this
Right.
this communication, this talk won't be possible without all these developments, right? To put it very simply.
Exactly.
So I have a couple of questions from one Mr. Ramanujam, and he wants to know, does quantum computers mimic brain synapses' ability to fire? Qubits, can they create biological sentience?
Way out of my league, that question. We had an earlier lecture by Dr. Prabha, right? Professor Prabha from IIT. She gave a talk. We can post the link of that talk. That person can. So I don't know anything about quantum computing. So it's nothing to do with human brain actually. So
okay. So the other question is, DNA is a bigger storage capacity than any computer in the world. Yet DNA computers are not popular. Why?
Manipulation. DNA is a chemical, right? Can you configure it? Can you etch? Can you do photolithography of a DNA? No. We are actually, people are, if people put resources into it, so you're talking about your computing. DNA is already doing that work, right? DNA is actually a one-time copying computer. Your RNA is, your human cell is actually millions of things that it's already doing. It's doing far more than computing. It's doing transport. You take any cell, any living cell, an amoeba cell, a plant cell, an animal cell, whatever. They're already doing hundreds of different, thousands of things without actually being computing. At the atomic level, we're not doing, that kind of manipulation. We want devices that we can handle, and so that's what's going to drive it. So if we can some way figure out a way to manipulate DNA the way we manipulate silicon, we probably
can I to add to that, can I say that we have just started with something called CRISPR, right? Gene editing technique, and we are at a very, very basic levels, and maybe once we get comfortable with CRISPR, maybe we can look at other things. But again, as you rightly pointed out, it is more about the storage and also about how easily you can retrieve and manipulate that, right? And if that is more difficult, then investing time and money in it is not going to be worthwhile.
Yeah.
If I can put it that way.
Yeah.
So it is way past our usual closure time, and it has been a very fantastic lecture. Okay, I think you covered a lot of topics, and you actually have left us with a lot more questions. Will you be sharing this PowerPoint slides, and can we ask you for some more lectures based on this as a follow-up?
Sure. Yeah, I can do that. I can share it. Actually, I teach this. It's one of the things I teach at this college, Savita College.
Okay.
So I had it fortunately.
Okay, so that explains the depth of the details that you have gone into. But it is, as I said, it is amazing. I have been in this industry for close to 25 years, and some of this is news to me. And I missed visiting the Computer Science Museum when I was in San Jose. So I will ensure that that is taken care of next time.
We should build one here too, right? So Bangalore, Madras, so much computing, we are doing so much software, we should build one too. Why should just leave it to California? We should have a computer museum here also. We may not get ENIAC and all that, but but we can use our devices. Perhaps we can do that here. I don't know.
So with that, we will call this lecture to an end, and thank you so much for all the participants who listened patiently. The video recording will be available, and if there are any specific questions that you want to ask Gopu, you can either ask it through the Varamira Science Forum FB group, or you can tweet us on Twitter, or we have a WhatsApp group. You can also ask us. We encourage questions, and we always want more conversations to be triggered by our lecture. So with that request, and we will also be telling you about our next lecture in due course of time. So thank you so much for your participation and spending your time with us on this evening. And Gopu, thanks a lot for this fantastic lecture. I personally learned a lot from this.
My pleasure.
I can't put it in words. To be very honest.
I learned a lot preparing for it too. So my pleasure. My pleasure.
Thank you so much.